Hello, and welcome to the video accompaniment for Chapter 8, Section 4 of our text. In this one, we're talking about permutations and combinations. And these solve, again, counting problems. And we'll use these principles that we've been developing, in particular the multiplication and addition principle, to help us figure out these types of counting problems that involve permutations and combinations. So after reading through this section of the book and watching this video, you should understand the definitions of permutation, R permutation, and R combination. You should understand where the formula, we're going to develop a formula for the number of R combinations of an n-element set. That's called CNR, or n choose R, denoted in these ways. We'll get to that. And we're going to come up with a formula for it. And so a really important thing in this class is for you to understand where that formula comes from. Again, so that you don't have to remember it, so that you can sort of synthesize it if you forget. And then you should be able to apply permutations and combinations to solve some counting problems. And we'll look at a couple examples of that in this video. All right, let's get started. So first off, a definition. A permutation of a non-empty set S is an arrangement or ordered list of the elements of S. So if you give me a set S, remember that starts off unordered. You can give it to me in any order you want. It's still the same set, but then a permutation of that set is an ordering of it. So assigning an order, assigning a place value to each element of the set. So for example, if I give you the set containing 1, 2, and 3, then we can find some permutations of this set. And here we want to find all the possible permutations. So one example of a permutation, so we're ordering these elements. So what if I just gave you 1, 2, 3? So that's an example of an ordering of the set S. I'll put it in parentheses to indicate that this is an ordered set. Or I could do something like 1, 3, 2. That's a different ordering, right? Because these are ordered sets, those two things are different. I could do 1, 2, 3. I could do 1, 3, 2. What else could I do? Well, I could maybe start with the element 2 and then do 1 and 3. I could start with 2 and then do 3 and 1. And finally, I could start with 3 and do 1, 2, or 3 and then 2, 1. So each one of these is a permutation of S, and there are a total of 6 of these. Are 6 permutations of S. So there will be some situations where we don't just want an ordering of the entire set S, but rather just to select few elements, just some ordering of some number of elements from a set S. And that's the idea of an R permutation. So R telling us the number of items that we want to be ordered. So an R permutation of a set S is an ordered list of R elements of S. And then the number of R permutations of an n element set is denoted P of nr. So for example, last time we looked at the set 1, 2, 3 and we gave all the permutations of that. That would be the same thing as 3 permutations of the set S, because there were 3 elements in S and we wanted ordered lists of 3 elements. In this example, we have S equal to, we added an element onto this, we have 1, 2, 3, 4, and we want to know all the 2 permutations of this. So that's ordered lists of 2 elements of S. So what are all the 2 permutations of this? Well, we could go, 1, 2, 1, 3, 1, 4. That's all the ones that start with 1. We could start with 2. We could go 2, 3, 2, 4. And we could even go 2, 1. Remember, 1, 2 is different from 2, 1. We could also start with 3. We could go 3, 1, 3, 2, 3, 4. Notice I can't repeat elements. So this isn't the same thing as a cross product, S cross S. I can't repeat the same elements. I'm listing out the elements of S, and so there's no repetition here. So that's an important detail. So it's, for example, you don't see 1, 1, 2, 2, or 3, 3 appear anywhere here. 4, 1, 4, 2, and 4, 3 would be the ones that begin with 4. And so it looks like there's a total of 12 permutations here. 12, and specifically 12 two permutations of S. Now, you should realize that it doesn't matter what these elements in S are called. All that matters is how many elements are in there. It'll change how these look, but they'll be the same number of them. And that's why we can define this number PNR regardless of the specific set, just the number of elements. So if a set has n elements, how many R permutations are there? So in this case, we just calculated, we had a set with 4 elements. So we calculated the number of 2 permutations of a 4-element set, and we found that that was 12. So what we'd like to do is come up with a formula. So given n and r, what is this number based on n and r? All right, how can we do that? Well, we have this theorem. Number of r permutations of an n-element set is, so P and R is n times n minus 1 times n minus 2 all the way down to n minus r plus 1. So this formula should seem familiar to you. This is also the number of one-to-one functions from the set 1, 2, 3 up to R to the set S. So why are these the same thing as one-to-one functions? Because that's really what an ordering is, right? If I have a set like, let's say A, B, and C, and I give a permutation of this thing, so for example, A, C, B, well, I can associate with this a function, a one-to-one function from the set 1, 2, 3 to the set A, B, C. And so that would look like 1 and A. So I put A in the first place. The second place is C. And the third place is B. And so we could go about proving this thing by associating it with this one-to-one function from 1 through R to my set S. But let's prove it in a slightly different way. And in fact, we'll just use the same argument we used for the one-to-one functions. We'll just use the multiplication principle. So I want to come up with a procedure. First, we're given S, which has n elements. And our procedure, what do we want to produce? We want to produce produce an ordered list of R elements from S. So it's an ordered list, so I'm going to draw, this is like the license plate, right? There was an order to the license plate, and so I have these 1, 2, 3, 4, up to R, different places that I can put my elements of S. And so how many ways are there to fill out this list? Well, so for the first element of the list, I have n different choices because there's n elements in my set, so n here. And then for the second one, well, I've already used the first element. And since there's no repetition allowed in permutations, right, I'm listing an element of the set, I can't use the first element that I already picked. And so there's only n minus 1 choices for this. And then the third choice, well, I've already used 2 available choices, so I have n minus 2 choices. And so on. I'd have n minus 3 for the fourth. And finally, for the rth spot, right, this is 1, 2, 3, 4. For the rth spot, I would have n minus r plus 1 choices, since I've already used r minus 1 elements from my n element set. And so what do I have left? I have n minus r plus 1 elements. And so this tells me this is n times n minus 1 all the way down to n minus r plus 1. Now remember, back to those one-to-one functions, we wrote this in a particular way, in a more compact way using factorials. This is the same thing as n factorial. So that's n times n minus 1 all the way down to times 2 times 1. And if I divide that, if I cancel out all the terms that are n minus r or less, So if I divide by n minus r factorial, I'll achieve this product here. And so that's exactly what PNR is. This is the same thing. That's what PNR is in general, the number of permutations of an n-element set. Now notice what happens with just a permutation. So number of permutations, so that would be, remember, a permutation is an ordering of the entire set, and so there my R would be n. And so this would be PNN, and I can use my formula I just figured out to see that this is what? N factorial over n minus n factorial. So that's n factorial over 0 factorial. We have to be careful here. 0 factorial is actually 1 by definition. And so during the activity for this, you'll see why we should consider 0 factorial to be 1. For now, you'll just have to take it. You'll just have to trust me that really is the case, that 0 factorial is equal to 1. But at any rate, we can derive the formula for just permutations based on this more general formula for R permutations. So let's take a look at an example involving R permutations. The King's Head Island Grand Prix. So there's this go-kart race on an island, and let's say there are a total of 8 racers. So a go-kart is just like a little, if you're unfamiliar, it's just a little cart that like typically kids can drive around, and in this case they're racing. So there's a total of 8 racers in this race, and I want to know what are all the possible outcomes of this race. So an outcome of the race would be an ordering of all of the racers, right? I want to know who comes in first, who comes in second, who comes in third, all the way down to who comes in last place. And so the outcomes here, right? It's an ordering of the racers. Since there's 8 total racers, I want all of the permutations of that 8-element set. And so this would be P8, 8. That would be the number of outcomes. And we know that that's the same thing as 8 factorial. So there are 8 factorial total ways that this race can end. 8 factorial outcomes for the race. Okay, but typically races don't care about all of the racers. Typically there's a first, second, and third place. So let's say the first place finisher receives a gold trophy, second place receives a silver trophy, and the third place receives a bronze trophy. We want to know how many possible outcomes are there for these first, second, and third place finishers. So we'll forget about the places 4 through 8. Forget about those. We don't want to count those different variations. We just want to know how many ways are there to have these first 3 finishers. And so in this case, I'm just ordering 3 racers out of the total of 8. And so this would be P8, 3. And we can use our handy dandy formula that we just developed. This is 8 factorial over n minus r factorial, so that would be 5 factorial. Notice that this is the same thing with the cancellation. This is 8 times 7 times 6, or 8 times 7 times 8 times 7 times 6, or 336. So those are all the different ways that we could pick a first, second, and third place finisher. So all those different outcomes for the first 3 places. Notice in each one of these examples, order was very important, right? First, second, and third, or just an ordering of the racers. In every case, it was ordered, and that meant permutation, because that's what a permutation is. It's an ordered list. So what if we don't want them to be ordered? Well, let's take a look at an example. So I'll use this example to motivate the definition of combination. So let's say there's this middle school, Wagstaff Middle School, that needs hall monitors. Let's say they need 3 hall monitors for this school year. So they make this announcement asking students to sign up. And they find that 10 students have signed up to be hall monitors, but they only need 3. So how many ways can they select 3 hall monitors from this group of 10 students? Now notice this problem, there's no ordering involved. We just want a group of 3 students. We're not sort of saying, number 1 hall monitor, number 2 hall monitor, number 3 hall monitor. We just have a group of 3 hall monitors. And so how many ways can we do this? So this is not the same thing as a permutation. This is something called a combination, because order is irrelevant here. We just want a set. And so we'll come back to this one. Yeah, right, yeah, we'll come back to this one once we develop combinations. All right, so what's a combination? Again, we start with an n-element set S. An r-element subset of S is called an R combination. So that's what a combination is. That's what an R combination is. It's an r-element subset of S. So back to the hall monitors, we had 10 students that signed up. We wanted to know how many 3-element subsets can we make out of that 10-element set, because those 3-element subsets are exactly the hall monitors that we select. The number, so a little bit of notation, the number of R combinations of an n-element set is denoted CNR, or this notation here, which I will use quite a bit. So parentheses NR. Notice it's not a fraction. There's no fraction bar there. It's just N. We say N choose R. That's the number of R combinations. But remember, an R combination is a R element subset of S. Some other names for this, we could also call it an R selection, or and this is really telling, it's an unordered list of R elements. We don't care about order with these. So let's take a look at an example. So let S equal the set 1, 2, 3, 4, 5. Find all 3 combinations of the set S. And then we'll use this to calculate what C53 is. Remember, that'll be the number of 3 combinations of the set S. So find all 3 combinations. This is all the 3-element subsets of my set S. So let's start building these. My combinations would be, well, let's say we do 1, 2, 3. We can put that in there. We could do 1, 2, 4. We could do 1, 2, 5. Notice I can't do 1, 3, 2, right? Something like 1, 3, 2 would be the same thing as this because they're unordered. So I've really used up all the ones with 1 in them. There's no other way. Oh, no, there's a few others, right? What if I did 1, let's say 1, 3, 4. 1, 3, 5. And what about 1, 4, 5? We haven't done that one yet. 1, 4, 5. And then we could do, say, we've used up all the ones with 1 in them. 2, 3, 4. We could do 2, 3, 5. We could do 2, 4, 5. And that's all the ones with 2 in them. Oh, is it? Let's double check ourselves. 2, 3, 4. 2, 3, 5. 2, 4, 5. Yep. And then let's see. What about 3, 4, 5? That seems to be our last one that we could do. 3, 4, 5. And that's it. That's all of them. So how many are there? Remember, these 2 were the same. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So so this is the whole list of 3 combinations of my set S. And then we can say now that we've counted the number of them, that this is C, so n-element set, so 5-element set, and we did 3-element subsets, so C53. We could also notate this by 5 choose 3, like that, is 10. So just like with permutations, we'd like to come up with a way to do this in general. That is, if I'm given n and r, how many r-element subsets are there of my n-element set? I'd like a formula in terms of n and r, just like I had for permutations. So let's develop that. All right, how can we find this combination formula? We want to give an expression for CNR in terms of n and r. And so what we're going to do is we're going to use a combinatorial argument to do this. So this is the first time I've used this term, combinatorial argument. What this means, any combinatorial argument, it means you're going to count the same set of things 2 different ways. And since you counted the same set of things, those 2 things must be equal to each other. And then you can use that equation to find some formulas or to solve problems. And so this is the idea of a combinatorial argument. So in this case, what we're going to do is we're going to count the number of R permutations of an n-element set S. So we're going to count the number of R permutations of the set S. You might be wondering, well, Drake, we already did that. or Professor O, we already did that. We said it was P and R, right? So on one hand, we know that this number is P n R, and we came up with a formula for that. This is n factorial over n minus r factorial. So this is what I mean by counting it two different ways. We already have a way to count the number of r permutations, and we know what the formula is. It's this, n factorial over n minus r factorial. So how can we count the number of permutations differently? Well, let's set up a procedure. Procedure, so produce an r permutation of S. So what I'll do, since now I have this notion of combination, what I'll do is, so task 1 here, I'm going to produce an R combination. So I'm just going to pick an R element set first, and then I'm going to order the R combination. Remember, the R combination will just be a set, and then I can do a permutation of that set. And there'll be a lot of different ways to do that, and a lot of different ways to pick my R combination, right? And so we'll see what we get if we do it this way. So for example, right, so if I want to produce a 3 permutation of the set, let's do an example just so you can see what I'm talking about. Let's say we have the set 1, 2, 3, 4, 5. If I want to produce a 3 permutation of this, so let's say R is 3, well, I could just order 3 elements of this, or I could first pick a set of 3 elements. So let's say I pick 1, 3, and 5. So this would be T1 is to pick this set. And then from there, I will do task 2. I'll order that. And so there's several ways of doing this, right? I could do 1, 3, 5. I could do 1, 5, 3, and so on. I could do all the different permutations of the set. And each one of these possibilities at the end here will be a 3 permutation of the set S. And so that's how this procedure works. And so let's see what this produces. Let's use the multiplication principle to figure out how many ways there are to do this procedure, to produce an R permutation of the set S. Okay, so step 1, we want to produce an R combination. How many ways are there to do that? So there are n choose R ways to do that. This is the formula we're trying to get a hold of, right? We don't know what it is yet in terms of n and R, but we can write it down because we have notation. So we'll do n choose R. That'll tell us, that'll give us a set, and then we'll order that. Okay, we'll order that. Remember that these are going to be, in this case, there's a 3 element set, and then we ordered that. So there should be 3 factorial different orderings down here, right? Because we had a 3 element set. In general, our R element set will do a permutation of that, and so there should be R factorial ways to take my set and arrange it. So this will be n choose R, number of ways to do T1, and then number of ways to do T2 is R factorial. So on one hand, we found the number of R permutations was this number, n factorial over n minus R factorial. On the other hand, we saw it was equal to this. And so what this means is that they have to be equal to each other. We counted the same thing, the number of R permutations. And so these two things are equal to each other. And I want to solve for n choose R. That's my goal here. And so it follows that n choose R, if I divide both sides by R factorial, this is n factorial over R factorial times n minus R factorial. Pretty neat, right? And so that's the theorem, that if we want the number of R element subsets of an n element set, so in other words, if we want the number of R combinations of an n element set, that number is n factorial divided by R factorial times n minus R factorial. So that's how we can calculate this in general. Now, a lot of people have probably seen permutations and combinations before. So notice the attention we're taking to rigor, to setting up the definitions and applying our counting principles. So the big takeaway I want you to get from this is to be able to understand where this formula comes from, to be able to derive this thing yourself. Because that's what I think is going to benefit you, is these types of arguments. Let's just go ahead and take a look at an example here to make sure we're understanding what's going on. How many 3 element subsets of S are there? So this is just like the hall monitor problem that we didn't solve last time because we didn't know what n choose R was in general. So these 10 are my 10 students that signed up to be hall monitors. And the 3-element subset, this is a selection of hall monitors. So it's just like that other example, only this one's a little more abstract. But hopefully you're starting to see how these definitions of combination permutation, they're abstract so that we can apply them to a lot of different situations. And so how many 3-element subsets of S are there? Well, we could start counting them, like, all right, 1, 2, 3, 1, 2, 4, 1, 2, 5. We could count all of them, or maybe we could get a computer to do it and then count them. But that's silly because now we have a formula for it. So let's see how to apply this formula. So this number would be C10, 10 total elements, and we want 3-element subsets. So this is C10(3). We could also write this as 10 choose 3. And so this is 10 factorial over 3 factorial times 7 factorial. So the 10 factorial over 7 factorial, that'll leave me with 10 times 9 times 8. All those other ones got canceled out, divided by 3 factorial, which is 3 times 2 times 1. Notice there's some cancellation. I don't necessarily need a calculator to calculate these things, even when they're big. So notice the 2 and the 10, those cancel off to produce a 5. The 3 and the 9, those cancel off to produce a 3. So it looks like what I have here is 5 times 3 times 18. So 15 or 5 times 3 times 8. So 5 times 3 is 15. Multiply that by 8, we get 120. And so that's how many ways there would be to pick these 3 hall monitors from the 10 students that signed up. And in general, the number of ways to select a 3-element subset from these 10 elements. That's a combination. All right, let's take a look at another example. This one may be a little bit more fun, might require a little bit more thinking. So let's say we're trying to remember a 7-digit telephone number. And we recall that we know the first digit is a 7, and then there are 3 1s and 3 3s in some order. We don't know what order, but we remember, yeah, there's 3 1s and there's 3 3s in this number, and the first number is 7. And so how many different telephone calls would we have to make to be certain that we finally call our friend's telephone number, right? Or if we were searching for all the telephone numbers, how many would we have to look at in order to be guaranteed one of them is our friend's telephone number? And so let's start setting this up. So we have a 7-digit number, 1, 2, 3, 4, 5, 6, 7, and we know the first digit is a 1. And then we know in here, these last 6 digits, 3 are the first digit is a 7. My bad. The first digit's a 7. I think I said 1 in row 1. I mean, the first digit is a 7. And then there are 3 1s and 3 3s. 3 are 3s and 3 are 1s. So of these 6 slots, we want to choose 3 of them to put the 3s in, and then choose 3 of them to put the 1s in. Of course, once we choose the 3s, then there won't be any possibilities to fill in the rest of them. The rest would just automatically be 1s, and there'd be only one way to do that. So for example, if we had the number like 7, let's say I choose the first 3 to be 3, 3, 3, 3, then I know that these numbers would all have to be 1s, and there's only one way to fill that out once I pick the 3 3s. And so really the answer is, how many ways are there to choose the 3s in these 6 slots? So there's 3 3s and there's 6 total slots, and so the number of telephone numbers is 6 choose 3, or let's actually calculate that. 6 factorial over 3 factorial times 6 minus 3 factorial, that's another 3 factorial. 6 factorial and 3 factorial gives me 6 times 5 times 4. We have another 3 factorial on the bottom, but 3 factorial is 6. And so these cancel out, and we can calculate that this is 20. So the student, actually, this isn't too bad of a situation for the student. They only have to try 20 telephone numbers to figure out their friend's number. All right, that's it. There's a lot more examples of permutations and combinations in the next section, some more applications of this. As well, there are some really neat properties with permutations and combinations, and particularly really neat properties with combinations. So for example, if I computed 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3, well, I could calculate all those. 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1, 4, I would get 8. And notice that that is 2 to the third. This is not a coincidence. If I did 4 choose 0 plus 4 choose 1 plus 4 choose 2 plus 4 choose 3 plus 4 choose 4, I would get 16, or 2 to the fourth. And so one big question is, why is this happening? Why is this a power of 2 no matter what n I pick? And so you'll have a chance to explore and explain these properties, to learn why they're happening and then be able to explain them to yourself and to other people. And that's going to be the activity for this chapter, is to explore these different things. It'll culminate in the creation of Pascal's triangle, which places all of these combinatorial coefficients, these n choose r's, in a really nice diagram. So that'll be fun. You can look forward to that. All right, that's it.